Ernest Lawrence, a professor at the University of California, Berkeley, also known for his work on the Manhattan Project alongside J. Robert Oppenheimer, invented the cyclotron in 1932. The inspiration for this innovative device came after reading an article on linear accelerators, discussing their limitations in terms of functionality and space. The problem with linear accelerators is that they required a lengthy discharge tube and extremely high potential difference, a potential difference which would jump onto the small amounts of air particles that remained in the vacuum chambers, as well as the fact that they could only accelerate the particles once in a straight line, requiring oftentimes a very long line. While envisioning the cyclotron, Lawrence thought of bending the particles' linear path into a spiral, enabling multiple accelerations, thus achieving higher energy levels at a fraction of the cost. The cyclotron consists of two hollow electrodes named Ds, which are pretty much always held in a vacuum. Between the two Ds there is a gap wherein the potential difference can accelerate the particles. As an alternating current is used, however, the polarity of the potential differences reverses frequently. Consequently, there is a strong magnetic field vertically perpendicular to the Ds created by two electromagnets. The two electromagnets, which are both equally attractive, apply a uniform force perpendicular to the particle's velocity regardless of its location in the cyclotron. This is due to the behavior of charged particles around magnetic fields, causing centripetal acceleration, much to the same effect as ion filings around a stick magnet. If a charged particle is placed in the middle, it will be attracted to the D that has a lower potential, accelerating it. The strong magnetic force causes centripetal motion, turning the particle back towards the gap. As alternating current is used, the polarity of the Ds can be reversed. If it is reversed, the particle that will chase the opposite D, which will now have the lower potential, accelerating it further. As the charged particles are accelerated between the Ds, they will spiral outwards due to the magnetic field, thus achieving multiple accelerations. The electric field transfers kinetic energy to the ions. The transferred energy can be calculated by using the work function W is equal to Q delta V, where Q is the charge of the particle, or EK is equal to 1 over 2 mass times velocity squared, where EK is the kinetic energy in joules. The radius of the path taken by the ions can be calculated by using the function R is equal to mv over qb, where B is the strength of the magnetic field measured in teslas. By adjusting the frequency of the alternating current in the electromagnets to match the frequency of the particle's circular motion, the polarities of the electromagnets can be reversed exactly when required, meaning the electromagnets continuously provide a force to accelerate the particles. The period of the alternating current can be calculated by using the function T is equal to 2 pi m over qb, where T is the period. However, the polarity of the Ds flip twice every revolution, meaning the period has to be halved. This can be rearranged to find the frequency of the alternating current, considering the fact that T is equal to 1 over f. When the frequencies of both the electric field and the particle motion match, the polarity will reverse exactly when the potential difference reverses. We can find the kinetic energy of an ion as it emerges from the cyclotron using this formula, where the kinetic energy is equal to half of the mass times velocity squared. However, knowing the velocity is equal to the radius of the cyclotron times the charge of the particle times the magnetic field over the mass of the particle, we can substitute it in. Kinetic energy is half of mass times the radius times the charge of the particle times the magnetic force being applied to the particle over its own mass squared. The first operational cyclotron had a radius of 6.25 centimeters and a magnetic field strength of 3 teslas. It accelerated individual protons from an ion source. Its exit kinetic energy can be calculated as follows. By substituting the mass of a proton as well as the charge of a proton, as well as replacing B, the magnetic field strength, with 3 teslas. There we can see that the kinetic energy on exit for this proton would be 2.69 times 10 to the power of negative 13. By using a part of that formula, we can also find out that the exit velocity is 8.9792 times 10 to the power of 8 meters per second, which is 0.334 times the speed of light. Ever since its successful implementation, the cyclotron has become indispensable in many scientific fields. In medicine, it is primarily used in the production of radioisotopes for the diagnosis of cancer and treatment, particularly in cancer ongoing care. In addition, cyclotron has played a pivotal role in the advancement of nuclear physics, serving as a powerful tool for exploring and understanding the atomic structure, ushering in an age of particle accelerators that have been instrumental in discovering previously unknown particles. By bombarding stable isotopes with accelerated protons, neutrons, or other particles, the cyclotron initiates nuclear transformations, producing a diverse range of radioisotopes. These radioisotopes are indispensable in medical treatments, industrial processes, and scientific research. Radioactive sources are used in brachytherapy to deliver targeted radiation to tumor sites, minimizing damage to surrounding healthy tissues. Additionally, radioisotopes are employed in radionuclide therapy, where specific isotopes selectively target cancer cells, leading to the destruction while sparing healthy cells. Beyond medicine, industrial applications of radioisotopes include radiography for flaw detection in minute materials, sterilization of medical equipment and food, and traces for the investigating of complex chemical processes. One of the most commonly used radioisotopes made using the cyclotron is fluoride-18, which is an ion created by splitting the nuclei of a oxygen-18 atom. The reason it is so useful is because this particular isotope releases or emits positrons. To understand why radioisotopes are used in those settings, it is important to understand the concept of an anti-electron. Positrons are indeed antimatter counterparts of their electrons, possessing the same mass but carrying a positive charge instead of the electron's negative charge. When a positron collides with an electron, they annihilate each other, releasing their combined energy in the form of photons that are often very high frequency. The phenomenon of particle-antiparticle annihilation is at the heart of the cyclotron's biggest applications. Positron emission tomography, or PET scans. PET scans have revolutionized medical imaging, providing invaluable insights into the functioning of organs and tissues at the molecular level. In PET imaging, a radioactive isotope, such as fluoride-18, is injected into the patient's body. The positron emitted during the isotope's decay travel a short distance before encountering electrons within the body. Upon collision, the positrons annihilate the electrons, producing a pair of gamma rays that move in the opposite directions. Sensitive detectors placed around the patient's body can capture these gamma rays, allowing the creation of detailed images showing the distribution of the radioactive traces. These images offer essential diagnostic information, aiding the early detection and precise location of diseases like cancer, neurological disorders, and cardiac conditions. Found at almost all major hospitals today, the cyclotron revolutionized nuclear science, enabling technologies like PET scans for medical imaging and providing vital radioisotopes. Its structure, with the powerful electromagnets and oscillating electric fields, ensures a remarkable particle acceleration and stable orbits.